In this video, we're going to take what we know about rational exponents and exponent properties and put it all together. Simplify. How do we simplify the square root of 28 divided by the square root of 7? Well, since we are dividing with the same root, you can divide the radicands and keep the root, right? So the radicands would be the values underneath the radical. So the square root of 28 divided by the square root of 7, first off, I think it'd be easier to see it like this. So the square root of 28 divided by the square root of 7 is really able to be looked at sort of like 28 over 7, which is the square root of 4, which is 2. Done. Again, we want to be able to do this, sans calculator, without a calculator. So we got the fourth root of 28 divided by the fourth root of 4. So again, that's the fourth root of 28 over 4, which is the fourth root of 7. So you can leave that as the fourth root of 7, or you can say that that's 7 to the 1/4 power. Now, how do you know which one to do? That would be something more in the instructions. It says to keep the root, so I think that this is more likely the answer the author is looking for. If we can divide when we have the same roots, the same goes with multiplying, right? As long as it's the same root, you can multiply the radicals or radicands and keep the root. So the square root of 5 times the square root of 7 is the square root of 5 times 7, which is the square root of 35. And then I kind of look for a perfect square within there. And there isn't any, right? 5 times 7 is 35, or 35 times 1. So that's just going to be the simplified version. Again, or 35 to the 1/2 power. Down at the bottom here, we have the fourth root of 3 times 6. So that's going to be the square root of 3 times 6, which is the fourth root of 18. And there's, 9 times 2, right? So perfect square in there, sure, but no perfect fourth roots. So that's just how we're going to leave the answer. So square root of 35 and fourth root of 18, and that's that. Now, just one more example. If you had the fourth root of 2 times the fourth root of 8, that would be the fourth root of 2 times 8, which would be the fourth root of 16, which is a perfect fourth root. That would have been 2, just for the record. Always look for any kind of simplifying of the root you can at the end. Now we get into the more complicated properties, product of powers. So remember that your x to the m times x to the n is x to the m plus n. So it looks like we have a 5 to the 1/2 times 5 to the 3/2. So that's going to be 5 to the 1/2 plus 3/2. Now, since those fractions, right, have the same base, that means that, the same denominator, it means that I can add them. So that's going to be 5 to the 4/2, which is 5 squared, which is 25. Again, just taking little bites as we go. So the first thing we did is we assessed, can we add those fractions together? Yes, they have like denominators. We add the numerators. We get 4 divided by 2. 4 divided by 2 is 2. And then I evaluate 5 squared because I can. Next on the chopping block, we have power of a power. Okay, so that's going to be x to the m raised to the n is x to the m times n. So for our example, we have 3 raised to the 5/2 power. And all of that, oops, let me fix that. All of that is getting raised to the second power. So first things first, we say, well, that's going to be 3 to the 5/2 times 2. Now, technically, that 2 is over a 1, right? And I can cancel these 2's. So that's going to be equal to 3 to the 5th power, or 3 to the 5 over 1, and 3 to the 5th happens to be 243, because we can evaluate 3 to the 5th. It's not a decimal answer, it's not an irrational answer, so we will evaluate it because it's clean. And our last contestant is the power of a product. So xy raised to the n is going to be both x raised to the n and y raised to the n. So we have 16 times 9 raised to the 1/2. So that's going to be 16 raised to the 1/2 times 9 raised to the 1/2, which again our 16 to the 1/2 is the square root of 16. So the square root of 16 times the square root of 9. I could multiply the 16 times the 9 and get a big number, but that's not necessary because the square root of 16 is 4. The square root of 9 is 3, which is 12. But by the way, the square root of 16 times 9 is 144, and the square root of 144 is 12. So I guess it depends on how you see it, but I like to keep the number small when I can. Work smart, not hard. As we move into the quotient of powers, remember that x to the m divided by x to the n is going to be the numerator x m minus n. So we see 4 to the 5/2 power, so that's 4 to the 5/2. Same base, so that's going to be minus the 1/2. As long as those are like denominators, we can subtract it. So it's going to be 4 to the 4/2 power, which is 4 squared, which is 16. And then the power of the quotient, we have x raised to the m, or x divided by y, all raised to the m, so that's going to be x to the m divided by y to the m. All right, and so we have 27 to the 1/3, so that's going to give us 27 to the 1/3 divided by 64 to the 1/3. So again, you could look at this however you'd like. I see this as the cube root of 27 over the cube root of 64. 3 to the 3rd is 27, so that's 3. The cube root of 64 is 4, so that is going to be 3/4. All right, so let's put this into action. So these are actually the exponents, and they're both the same base. So for a, that's going to be 2 to the 3/4 plus 1/2. It's the same base getting multiplied, and we're going to add. Now the problem is we can't add those because they are not like denominators. So 3/4 added to the 2/4, because that is the re-expressed mathematical equivalent. Now again, this is where if you don't know how to deal with fractions, that's not what this video deals with. If you need help converting fractions so that you can add them, subtract them, and whatnot, then see me for help, and I can do that. In this video, I won't be covering that. I'll just be handling it as if there were no problems. So that's going to be 2 to the 5/4. And then that technically is the 4th root of 2 to the 5th power. And technically, that is 2 4th root 2. So both this answer and this answer are good final answers. I think that we will default to this, seeing that we started in rational or fractional exponents, so we will end in a fractional exponent answer. Let's move on to B. B has us using sort of all three components of the products and powers together. So what I see here is that we have the same bases getting multiplied, and so that means we're going to add those exponents, but the problem is we're also raising a power to a power, right? So there's all kinds of stuff going on. So first thing we're going to do is deal with the 1/3 getting raised to the 3rd power and the 1/4 getting raised to the 3rd power. So for B, we're going to say 5 to the 1/3 getting raised to the 3rd. That's multiplying. I'll put that over 1. Times 5 to the 1/4 times 3 over 1. That's going to yield us 5 to the 1st power, because the 3's cancel out. That's just 5. Times 5 to the 1 times 3 is 3. 4 times 1 is 4. 5 to the 3/4 power. Now we have like bases getting multiplied, so that's going to be, technically that's a 1. So a 1 in terms of fourths is 4/4, so that's 5 to the 4/4 times 5 to the 3/4, which is 5 to the 7/4. And that's a reasonable final answer. For our last problem, we have 3 divided by 3 to the 1/4. So technically this is 3 to the 4/4, because it's 3 to the 1st power as we're sitting over here. Technically that's 3 to the 1st power. So when I look at that, I say, well, I'm going to convert that to 4/4 so that I can apply my exponent rules of subtraction when I'm looking at division of like bases. So that's going to be 3 to the 4/4 minus 1/4, which is 3 to the 3/4. Done. Now you want to be able to do this without a calculator, right? But if you wanted to try to put, say, this into the calculator and then this into the calculator so that you see that you're getting the same answers, that's how you know that you have the same value, right? And what I mean by that is when we're learning fractions, 1 divided by 2 is equal to 0.5 and 4 divided by 8 is equal to 0.5. That's how you know that 1/2 and 4/8 are equivalent expressions. Or at least that's how you learn to start to trust yourself. And just moving along, so we have 7 to the 1/3 times 49 to the 1/3. Now the problem is these are not like bases. So I'm going to say 7 to the 1/3 times, and I'm going to re-express 49 as 7 squared raised to the 1/3. Now I have the power to a power, so I'm going to evaluate that part. So that's 7 to the 1/3 times 7 to the, I'm going to multiply those, and I'm going to get 7 to the 2/3. Now I can apply the addition rule, right? 7 to the 1/3 plus 2/3 is 7 to the 3/3, which is 7 to the 1, which is 7. Wow, that was a lot for just 7. Okay, let's move along to part B. Part B says I'm going to deal with my power raised to a power first. So I got 5 to the 1/3 raised to the 3rd. So that's just going to be 5 to the 1/3 times 3, which is 5. Or technically 5 to the 1, because 1/3 times 3 is equal to 3/3, which is 1. So then I have 7 to the 1/4 raised to the 3rd power. That's going to be 7 to the 3/4. And now seeing that these are separate bases, there's not much I can do. They have different roots, so that's just going to be it. For 20, first thing we're going to deal with is the powers raised to the power. So we're going to get 20 to the 1/2 raised to the 3rd, right? So that's going to multiply, and 1/2 times 3 is going to be 3/2 over 5 to the 1/2 times 3 is going to be the 3/2. Now again, if we have both of these to the 3/2, then that's going to be essentially 20 divided by 5 to the 3/2, which is 4 to the 3/2. So that's the square root of 4, square root of 4 cubed, which is 2 cubed, which is 8. All that for 8. Again, doubling back to B, there really wasn't much we could do in here to simplify the inside. They weren't like bases, so I couldn't add the exponents. And then after I had applied that exponent rule of power to a power, I was still left with unlike bases and unlike roots. So there really was just nothing we could do there. For this example, take a look at the square root of 8 divided by the cube root of 128. So the square root of 8 divided by the cube root of 128. Now, either way you look at this, this is 8 to the 1/2 divided by 128 to the 1/3. There's all kinds of problems here. Essentially, there's not much we can do. So we could evaluate the square root of 8 and evaluate the cube root of 128. But I think sticking with the transforming the radical into an exponential form, and then let's see what happens. So 8 to the 1/2 divided by 128 to the 1/3 power. Now 8 to the 1/2 power is 2 to the 3rd raised to the 1/2. And down at the bottom, 128 is 2 to the 7th raised to the 1/3. And so now we can deal with some exponent rules here. So that's going to be 2 to the 3/2 divided by 2 to the 7/3. And now we just got to deal with the fact that we have fractions with unlike denominators. So I'll draw your attention over to here. So 3/2 and 7/3 have a sixth in common. So what we're going to do is transform them into sixths. So 2 to turn into a 6 is times 3, so times 3 on the top. 3 to turn into a 6 is 2, so times 2 on the top. So that's going to be 9/6 and 14/6, which we are going to use the subtraction rule. So that's going to be 2. The numerator was the 3/2, so that's going to be 9/6 minus 14/6, which is going to yield us down here 2 to the negative 5/6, which is 1 over 2 to the 5/6. And that is our exact answer. So for this next example, we have 27 square root of. So it's going to be 27 to the 1/2 power times the 9 to the 1/3 power, right? Not like bases, not like radicals. So we got some problems, but I know I can re-express 27 as 3 to the 3rd, all raised to the 1/2, times 9 is 3 squared raised to the 1/3. So then we use our multiplication power rule, and we're going to have 3 to the 3/2 times 3 to the 2/3. And now we're going to add them, but we have to write some equivalent expressions here. So that's going to be 3 to the 3/2 plus 2/3. Can't add that, so it's going to be 3. We need them both to be over 6. So it's going to be 9/6 plus 4/6, which is going to give us 3 to the 13/6, and leave that as an exact answer. Now again, at some point you're going to say, why? Why do we have to know this? Again, Algebra 2 is the gateway course to upper level mathematics, and you want to be able to take items like this and to re-express them into items like this for more complicated situations to simplify things, make things easier to work with. All right, this next one's a bit of a doozy, but let's see what we can do here. First, let's open with those parentheses. 5 to the 3.5 divided by 5 to the 1.4 times 5 to the 0.5, all closed, raised to the 1/4 power. Now let's collapse the inside. Since they're all the same bases, all this is going to be raised to the 4th power. But this is 5, 5, and 5, so division here says that we subtract those. So 3.5 minus 1.4 is going to give us 2.1. And then we're going to add that to the 0.5. So we're going to add that to the 0.5. We're going to get 5 raised to the 2.6. And 2.6 raised to the 1/4. Now, the proper way to go about this is to take that 2.6 and recognize it for what it is. That's 2 6/10. 10 times 2 is 26 over 10. That's going to be 26/10. Reduced is 13/5. So now what I have is 5 to the 13/5 raised to the 1/4 power, which is 5 to the 13/20. And there's our exact answer. That one was certainly another big mouthful, but we knock it down one bite at a time. So our last one's not too shabby. Got the 4th root of the square root of 1024. So that's the 1/4 power of the 1/2 power of 1024. And really, square root of 1024 is 32. 32 to the 1/4 power. Well, the 4th root of 16 is 2, but the 4th root of 32 doesn't work out nice, so we're just going to leave that just like that. That's an exact answer. And that's all we got today. Hope you had a little fun.